Oh, you're right. Well, actually, here it. Now it should be working.
Okay.
This is very confusing for everybody in the room. I mean,
I'm so sorry.
Miriam, one of the head TAs, just informed me YouTube is not working, which of course is it's not unimportant to you, but important to everybody else. Is it working right now, Miriam?
Yes, it is. Thank you so much.
Because I can see myself, so it should be working. But...
Thank you so much.
Okay. Good.
Sorry to interrupt.
Okay. Well, thank you for interrupting me. Please do interrupt me again whenever necessary.
Yes. Thank you.
I can see your video, so you just wave if you need my attention.
Perfect.
Great.
Thanks.
Okay. Good. The wonderful world of hybrid teaching. And that's, let's hope that over the next few weeks, I get a little bit more professional at it. Good. Okay, so where were we? Prediction is impossible, right? Just by looking at, okay, what happened today and then predicting tomorrow, it's impossible. It's not going to work. Let's take then 2 days into the past, right? I mean, is there really a trend? No, doesn't work. But 3 days, nope, still essentially the same, right? I mean, that's I can flip those three settings back and forth. You won't see any difference. I mean, you will not be able to make any buck out of it. However, if you use a slightly more fine-grained analysis of the data, you choose the right variables and you figure out, well, the machine, you don't need to do this yourself, which features to use in what combination, well, what nonlinear dependencies are there, then actually it is possible to identify a weak trend. As you can see here, so based on the prediction of decrease, these two are slightly offset from one another. And if any hedge fund would find anything like this, they would be incredibly happy, and they would be in a few days the richest hedge fund in the world. But, in practice, what you need is really the tiniest of differences, and then try to exploit it. Right? If you can make with a trade 1 cent in each trade, and you just do this at scale, right? You invest billions in it, and billion times you make a cent. Well, that will get you rich, right? So the main point here being that the stock market is chaotic. It's very difficult to predict, but it's not impossible as long as you use the right features. Now, the sad thing is, and also the giveaway why you are not going to not going to become rich with this trick. This trick is known, so people are using this. And the moment the market uses it, then well, the only thing that you can achieve by doing this is not losing any money, but making money. That's not going to happen. Okay, so perhaps you will learn something that will earn you a few billion in a few years. Who knows? That I can't promise. Next application. Right now, we're going further and further away from pure prediction, and we're actually going smack in the middle of inference. We want to learn something about the data, but there's nothing that we really want to predict so much. So this is an example from bioinformatics. And what we have here, well, 64 cell lines, so cells that have been sequenced, and we measured all sorts of things. And each of these cell lines, these individual cells, well, they suffer from a particular brand of cancer, so to speak. Now, what we would like to find, which types of cancer are similar or more similar to each other than others. And if we can find, for example, here at the top, this blue, this blue blob over here, suppose that these are all cancer types that are, well, because the data, what I'm showing you may or may not be real. I mean, I hope you don't feel tricked. But if all these blue dots over here are really of the same type, then perhaps if we can find a treatment, a drug, or something against that alleviates this type of cancer, if we can find this for one, or we know which ones to apply it to next, right? That would be pretty cool. Well, this is a task that is not really predictive. It's more like, okay, put stuff together that belongs together. Well, just by phrasing it this way, you already hear that, well, this is a very unclearly defined task. It's very difficult to define. We'll discuss this relatively late in the course, or at least past halfway mark. The reason is that, yeah, it is indeed very subtle. And you first need to know some basics about how we can do this. And then we can get going with clustering. So besides that, it's difficult to tell what is now similar, what is dissimilar. Right? Suppose that we have magically, we're given, this is the right dissimilarity metric. How many groups do we see here? 4? 4, yeah, 4. If I would say 5, would you say that I'm crazy? It's possible to say, you know what? Well, this blue one I split into 2, right? I mean, here we have more a circular blob and here a longitudinal blob. I could, hey, well, are these now really green? Huh? Are these even a group, right? We can go very, very metaphysical, right? I mean, very philosophical. If this is a group, then, well, perhaps this is also a group, and that's all of a sudden we're at 6 or at 7 or at 8. So even if we are told, I mean, this is the distance, this is the dissimilarities between points, in this case, cancer cell lines, just even deciding how many groups there are is an incredibly difficult task. And in many ways, still a completely open research question. Let's see. So what I showed you was, well, it is indeed cancer data. How did we project it now into this 2D space? Because obviously, I mean, how would you put cancer data, sequence data, and whatnot into a plot, right? I mean, what we're doing here, we're plotting it along the first 2 principal components. Some of you may remember this from linear algebra. For others of you, this may be, well, maybe you've never heard about it, or it's a distant nightmare. Well, don't worry, we will revisit this nightmare in that, but in a nice way, not too much waking up screaming. Good. So, but that is essentially the axis system I have here. This is the first principal component, the second principal component. Those are the directions in your data that explain most of the variance. So they explain most of your data that is possible in 2 dimensions. The colors are now the actual different types of cancer. So you can also immediately see that, well, here we have circles, that is good. But here we have, well, what I like to call the mixed grill, right, on the menu. And that's, is this now truly a cluster? Is this a group of similar cell lines? I wouldn't say so, at least not under this labeling. But maybe there is some underlying structure that we don't know yet. And that is exactly the point, to figure out what are the structures in my data that me, as a domain expert, right? Typically, I refer to me as then the machine learner, and then we'll work with the domain expert. But the moment we can uncover some structure in the data that we didn't know about, this gives us a chance to, well, figure out, hey, wait a second. This group here, or this green group over here, let's try to find a targeted drug. Let's see if there's what the commonalities now really are. Long story short, this is all unsupervised learning, because we're not told what the exact goal is. Also called exploratory data analysis, which coincidentally is the name of my research group. So I can already tell a little bit where my heart truly lays. We're going to be discussing this in chapter 10. Good. Okay, well, that was a quick overview, not of everything, but a quick overview of some of the highlights that we'll be discussing. How can we do prediction? How can we do inference, figuring out what are the most important aspects towards prediction, as well as really exploratory data analysis? What on earth is behind the process that generated my data? Those are the 3 things you can expect during EML, and then a few other things on top of it, which we just throw in just for fun, just for kicks. Good. Let me, yep, okay, so Zoom is happy. I hope you're happy too. Good. Are there any questions so far? No? Okay. Does anybody say, okay, well, this is really not for me. I don't care about learning about my data. I don't care about getting rich. I want to leave. It would be fine with me. It would be fine with me. I mean, like I said, I would be sad by seeing the numbers drop, but then again, I don't want to waste your time either. Good. Okay, so that was the quick overview. Let me now continue with the actual introduction. Now I will explain a few things that hopefully you will learn a little bit. It's still the first lecture, so I'm keeping the temperature low. Good. Oh, and by the way, I should have done this on the first slide as well. ISLR, this magic acronym over here, is the abbreviation of the main book that we're using, Introduction to Statistical Learning with R, right? ISLR. The second one is Elements of Statistical Learning. So I presume that all of you watched the organizational video in which I explained which books we use and why we use them, right? If perhaps this is still on your to-do list, let me very quickly recap. We're using 2 books for a very good reason. ISLR is a great book, didactically really builds up concepts in a very careful pace, explaining not too much, but really at the right point. So that is our main text. And we'll be following this pretty much, well, hand in hand, chapter to chapter. ESL, Elements of Statistical Learning, is more, well, let's say the older brother / sister of ISLR, who went to the gym and perhaps took a few steroids too many. I mean, that's the scary version. It's the scary version. It's also the version of the book that you want to come with you if you have to go into a dark data science alley, right? I mean, that's then you rather have ESL with you than ISLR. So Can you survive this course with just ISLR? Probably, but you will have to do your best, right? You have to go to the gym yourself. What the best way to consume this course and to learn about these concepts also towards future courses is to first get the intuition from ISLR and then read up basically the same material, but written slightly more, let's call it professionally, in the ESL book, right? Does this cost twice the amount of time? Yes, in a way, because a few years back, we just used ESL. Well, then everybody needed at least twice or three times the amount of time to consume everything. And just using ISLR, well, yeah, like I said, I wouldn't dare sending any of you into this dark data science alley. So hence these two books, use them wisely. And both of them can be downloaded from the internet. It's also a nice coincidence. Good. So one of the running examples I'll be using throughout the next few lectures is that of advertising, right? We're still in the business of making money, but in order to make money, we need to advertise our product and such that in the hope that people will actually buy our product. I actually forgot what they're trying to sell, but it's not so important, right? It's the product. And we can advertise this product in different outlets, through different media, right? I mean, TV, that is like old-fashioned YouTube, right? I mean, you might remember, right? This box. Radio is like YouTube when the screen is broken. And newspaper is like, yeah, I don't know, the manual that you got with your laptop, but then you get a new one every day. I don't know. I used to read newspapers. Right now I read them on my computer. I used to watch TV and I used to watch radio. Yes, very good. I used to listen to radio, but these days, I mean, this example is perhaps slightly outdated. Anyway, some people do attend to this media and we want to reach out to them. And we need to choose what is going to be our advertising budget, right? I mean, are we going to advertise on YouTube and or Facebook and so on and so forth? Perhaps that's the more modern version of this. Now, the budget that we allocate per medium, that we're going to call this X. Well, that's this one over here, X. And well, there's different flavors of X. So we have X1, that's the budget we spend on TV, X2 on radio, X3 on newspaper, and well, perhaps we can add Facebook and the likes as well. I'll be calling these things, these X's, by different names. Perhaps didactically not so smart, but that's just been my brain is wired differently than the book wants me to. So the book speaks about input variables and predictors primarily. I try to follow this naming, but to me, well, if you have data, you have different features, or you have different columns, or you have different attributes. So whenever I say any of these words, I still mean these X's, right? There's also something that we're particularly interested in often in machine learning, and that is the output variable, which also has multiple names. It can be the response variable, it can be the target variable, it can be the dependent variable. And I probably come up with a few other variants throughout the next few weeks that will blow your mind. We typically call this one Y. The goal, what we're trying to achieve, is to predict, based on the information encoded in X, through some magic formula, the output. So in this case, we could assume that Y is actually, in truth, right, the mother nature or father nature or trans nature, I don't know, perhaps I'm pushing that too far, is somehow a function over X plus epsilon is some noise. And of course, this X we can unroll to however many predictors we have. Typically, I use P for the number of predictors. And this epsilon random zero mean just it's a nuisance. Good. So this is what we're trying to do, and this is how the setup that we're trying to assume right now. Well, what we could have a look at. Okay, well, how do the sales now depend based on how much we spend advertising on TV? Numbers are in thousands of dollars. I mean, it's not a local example. As you can see, the more we invest, the higher the sales are, right? So, okay, pretty good. So perhaps we should even invest even more in TV. What is the relationship here? So because we will be looking at also radio and whatnot, other media. I mean, we need to know, okay, well, how good is it actually, right? I mean, what is the best investment? You could say, well, you know what, let's just draw a line. I'm going to draw this line. Actually, this happens to be the line that fits this data best. And that's how we define best, and how to find this line we will see unlikely later today, maybe, and otherwise next week. Okay, so this is the slope of this line. It's pretty decent, right? Let's look now at the sales increase for radio, drawn in the same scale, at least the same Y scale, right? But the X scale is definitely different. What is the relationship there? Slightly less. Okay, now you already see, right? I'm trying to confuse you. My main game in teaching is always to confuse students, by the way. And those of you, the two of you who already know me, know this. The rest of you, like, what? Is this the best line? Yes, this is the best line, depending on how you define best. Let's see. Do I have a volunteer who, let's say, intuitively could identify a better line? Just anywhere. Yes, please. I'm trying to follow. So basically like this. Oh, the left one. Okay, yeah. Okay, yeah. So more like this. Okay, yeah. So a bit sort of sigmoidal kind of thing, right? Yeah, exactly. So an S shape. Okay, yeah, that makes sense. That makes sense. Okay, good. Okay, but now let's try to stick for now. It's a good example, but right now we're leaping a bit too far ahead into the course. But I appreciate the thought very much. Suppose that we stick with lines, with straight lines. And let's stick with the central example. Would you have a candidate a better line? Yeah, the gentleman behind you. Yeah, that will be you. Yes, yeah. So so this one. Okay, so okay, then perhaps my question was not entirely clear. So this line is according to some magic criterion that I will explain later. This is the best line. When I showed this, I saw many of you like, huh? Is this now, for your feeling, is this the best line? Or if you were to explain what is the relationship between spending on radio and the sales that we achieve, what shape, if you were to use, how would the straight line go according to your gut feeling? Because I'm pretty sure it's not this line. This would not have been the line that you drew. If you did, then either you're brilliant or something else. What is the line you would draw? Okay, good. That's what I meant to ask. It's more that, so for me, my gut feeling is that, so this slope, right? I mean, yeah, this indeed here at the end, there is way more spread, right? This is also what the gentleman in front of you. What's your name, by the way? Alex. What Alex tried to capture in the left plot to sort of follow the spread a little bit, right? And stay closer to let's say the central band of the spread, right? That's what you're trying to achieve with this. Now, this is what this line does quite well here, right? So there's lots of spread here, lots of spread there. However, you could also say that, hey, if we now look at how densely these points are distributed, then there is more of a band here at the top. And then, yeah, you just have lots of people who don't pay attention to radio anyway, right? It's just like music in the background. So perhaps this line should actually be more steep and you just have a higher spread at the bottom, right? Okay, let's keep that thought, right? I mean, so even if we have something as the best line, there may even be a better line, because it really all depends on how we define best. What are we trying to model, right? Good, let's continue. Spending, sales, or advertising on newspaper. What is the best line? I'm trying to find somebody on this. I know that both of you are eager, which I appreciate. Yes, you. Okay, so you're proposing to make it more steep, like this. Okay. Would anybody disagree if I would say, okay, there is no line at all, it's just flat? You in front? The data is indeed very spread out, yes? Okay, so you say it should not be that steep because it's very spread out. There's too much uncertainty, if I paraphrase, right? Okay, good. Gentleman behind you? Could we use some quadratic function? Yeah, okay, so, but a quadratic function typically has sort of this parabolic shape, right? Either like this or like this. And you see this in this figure? Well, okay, yes, that I don't know, right? I don't know. I mean, I have difficulty seeing it, but perhaps if I hold my, anyway, good. Thanks for the input. If we fit this best line, which explains most of the variance, we get actually quite flat line. But so mice say, okay, is there a line at all? Or is it just completely flat, right? Okay. The steeper one you could have done just as well, but indeed there is so much variance that there's very little information in how much we spend on newspaper advertising towards the sales. And when I say information, really mean explaining a lot of the uncertainty, right? I mean, you could say, of course, if you spend 100K, then hey, look, we get a lot of sales, but that is just 1 point. So it's very uncertain. Good. Okay, so let's look at a slightly different data set. We'll also see this multiple times. This is not real. The other data is actually real. And I think I should ask this question to Alex. What line would you plot here? Well, no, actually, no. So the reason I go back to you is because the previous answer might have been in the right direction. Nudge, nudge, wink, wink. Yes, exactly. So it will be something like this, this S shape that you were talking about earlier. But, indeed. Well, this is actually the line from which we generated this data. And we would like to try to find this based on the data, right? That is the goal, right? If we want to predict. So we're just given these points, what would be the function? Now, let me actually take a sip because lecturing is thirsty business. I haven't drank club mate in, I think, when was the last real lecture? seriously. I mean, club mate is my lecture drink, but otherwise, I don't know. Not sure that I can't say that I can't stand the taste, but this has this weird liquid cardboard taste, right? Do you recognize what I mean? Which somehow really works when lecturing, but on a daily basis is not my thing. Okay, good. Let's see. If I now draw from every data point the line to, so this horizontal line, I keep wanting to point to the screen, but that is unfair for the zoomers. So I'm going to do it like this. So a line towards the function that I'm trying to fit, right? Or in this case, the function that might actually have generated the data, but that we don't know yet. Now, just by looking at how many of the lengths of these black stripes, we can already get a bit of a feeling how good the function is that we're trying to fit the data with, right? So, of course, just as a thought experiment, suppose that I would have just put a line, straight line like this, right? Completely flat at 50. We would have gotten a lot of black stripes, long black stripes, right? Equally many, but stripes because every point generates a stripe. But this would be very long. Only these points would be very happy. And these long, right? So, okay, it would be a very bad line. It already gives also a bit of an inkling towards what would be now the best, I'm going back to you, Alex, what would be the best straight line, linear function? What would be the best one? Where would you roughly start? Which coordinate and where would you end? Mm-hmm. Okay, so something like this. Okay, good. Yeah, so that you're saying you're going after most of the density and trying to reach as many of the points as close by as possible, right? I'm putting words in your mouth now, which you should never do, right? And that, but exactly. So let's. I mean, I don't have this line here. I mean, it would be unfair for the people on Zoom if I would now redraw this on the board. But let's take this line and let's think about how many of these black stripes, or how long would the black stripes be compared to, well, the other options that we've seen. Here in the middle, here we probably the line that Alex would fit would it looks, this is almost straight, right? We get very short black lines, lots of very short lines. It's just here at the ends, left and right, where things go a bit haywire, right? And well, depending on how much data we have at the ends, right, at the shoulders of our data, that's really where things go completely bonkers. Now, that is already in a nutshell what we're going to be trying to do. We want to try to formalize how to minimize this overall error, this length of these black bars. So good. How do we do this? Yeah, y estimate f actually, well, I think we already established why. I mean, I probably moved the slide around a bit too often. We know why we want to predict, right? I mean, what we assume is that in general, these inputs X are available, but the output is not. And that's the one that we want to know, right? I mean, is something going to make us a lot of money? Yes or no? Is that going to be poisonous? Is it going to kill us? And so on and so forth. Now, what we hence want to do is we want to estimate. That's why Y is wearing a hat right here. Based on X, through some magic function F hat, what is now the actual value of Y going to be? Of course, we never truly know this function, this F. So we estimate this function, and hence F also gets a hat. Going back to the difference between prediction and inference, often we don't give a rat's ass of whether or what shape F takes, as long as it does its job, right? Okay, that is really the prediction case. Sometimes we do, and then things get actually both easier and harder. Now, let's forget that for a second. We're just interested in prediction, and we want to get the best function within a certain class that we can get. We want what is best. It needs to predict very closely, not short black lines, right? And we can measure this in many ways. What is a very natural way to do so is the following, namely to consider that F can make two types of error. The first error is reducible. Basically, if we would have a better approximation of the true function, we could do better, right? So if we have a shitty function, then then by going closer towards the actual shape, we will be able to reduce error. There's also what we call irreducible error. This is for a large part due to noise in the system. That could be that just like in the advertising example, there was this spread that maybe certain people just don't read the newspaper, and no matter whether you actually how much you spend on advertising, they're never going to buy your product, right? And they should basically cancel their subscription, and so on and so forth. There is noise in the system that we cannot model, and there is structure in the data that we can model. Reducible, irreducible error. By this idea, we can decompose the expected error. So this is the squared, or the square of the expectation of what is actually the value that our function should spit out, Y, and how far away is our guess, so Y hat, this squared. We can now unroll this like follows. So there is an actual function, magic function in the sky, which also combines, so this is the reducible error. The closer we get to the true F, the better we can do. There's also this epsilon, this irreducible error. No matter how hard we try, we will never be able to fit this. This is just noise, right? So we should split this out. And of course, then we can subtract what our expectation is, so our function is, and again, we look at the squared expectation. If we do a bit of math, bit of algebra, then we will see that here we have the actual function minus F hat squared. That's the reducible error. This is where we can hope to gain something, right, with regard to this term. And we still have, well, the irreducible part, which reduces just the variance of this thing. There are some assumptions under the hood, namely that this error has a zero mean. So it's not, well, basically we capture all structure that is capturable inside F. That is essentially what it comes down to. Expectation of all possible data, reducible, irreducible. And if you want to know if this is true and how to do this, well, you have to do your homework. Good. Last slide before the break. Another reason to do to infer F or estimate F is inference, learning about the data. We covered this a bit. Rather than treating this F hat as a black box, just fit it the best way you can, and I don't really care, what shape you use. We really want to understand what is the relationship. We want to be able to essentially look at it. So this is, for example, in bioinformatics the case. Suppose that we want to see what are the, I'm going to use the word causes. You always have to be a bit careful with the word causes, but what are the genetic causes for a certain disease, right? And as you know, many diseases are very complicated, right? If you have this mutation, then it's bad, but if you have the other one, then it's okay again, and otherwise, perhaps you need 3 that are bad. Complicated. we want to know which are these groups of mutations, right? What are the conditions? So maybe you have the wrong genes, but hey, you live a very healthy lifestyle. Everything is good. Well, lucky you. It could be that there's plenty of people who, well, unknowingly live the wrong lifestyle and suffer from this disease. Would be nice to figure out what advice to give them, right? Okay, so in all those cases, we would like to know what are really the driving factors. And just black box prediction is not going to cut it. Also, it's very easy to imagine that if we now want to predict, let's say not even the disease, but I don't know how tall somebody is probably going to be just based on their genome, right? I mean, stupid task, but okay, let's give it a go. How many genes out of the 20, 30,000 that have been identified in the human genome are going to be relevant for this? Your guess is as good as mine, but I think we can all agree, even without being biologists, we don't need all of them. Probably we need, well, probably a bit more than a handful, but I don't know, a few hundred maybe, and that's that, right? The rest, which is related to, I don't know, eye color, hair length, hair growth, right? As you can see in that, there's definitely some genetics going. Well, you can't see that, but if you would see the pictures of my dad and my grandpa, I mean, there's definitely some genetics going on. Which do we need? Well, we probably only need a few. Which ones are those? And what is now the relationship? Some of these genes will be more important than others. Is there a linear or a quadratic or a cubic or whatever exponential relationship? So all things that are very useful to know. Yeah, and exactly. So it's in gray. Sometimes this depends then also on the other predictors. Sometimes there is a very acute interplay, right? If you have these three mutations, then it does this, but otherwise it does that. Yeah, we don't want to have this buried in the black box. So already asked. So yeah, to go back to the advertising example, which media actually have an effect on sales? We already saw that newspaper doesn't seem to do so much. TV seemed to be pretty good, right? Well, and radio was a bit in the middle. But it could well be that if we don't advertise in newspaper, then which doesn't drive sales by itself, then when people hear the name on the radio, they won't know it and they won't buy it. So maybe there is an interplay there, right? So which ones really contribute to sales? How can we tease this out of data such that we can generate the biggest boost? Okay, good. Like already covered, prediction, inference, in a way are two sides of the same medal. And yeah, I prefer the inference side because black boxes, I mean, who cares about them? At the same time, I think perhaps 99 out of 100 applications of machine learning and AI these days all derive on black boxes. And you already know the name of the black box, probably, I mean, deep learning, which is an amazing black box. And if you hold it just right, it can do beautiful things. But if you hold it and slightly differently, it will break down fantastically. And yeah, that I personally don't find so. I find it exciting, but also scary. Using it in the right setup, knowing what something is doing, well, that is what a lot of research is all about these days. But, EML is a relatively basic course, right? So we will, near the end of it, touch upon neural networks and deep learning. But what we will be mostly focusing on are really what are the elements of machine learning, what are the basic building blocks, right? Good. Okay, it is 5:02 right now. Let's take, well, here it's 5:02, there it's 5 exactly. Let's take a 15-minute break, either to get a bit of oxygen into your brain or whatnot, stretch your legs, and then we start again 15 past. Good. And we're back. Okay, so let's see. Yes, it works. Okay, good. It is 15 past here. It's 14 past there. I'm completely refreshed to the point of being actually a little bit cold. And that's perhaps I should have worn my proper jacket outside. Let's get started again. I mean, welcome. Please find a seat. Good. Okay. So let's go back to, well, we want to estimate this function f that is underlying our data, right? Be it because of prediction, be it because we want to learn something about the process behind our data. So how can we do this? And what difficulties will we face? Will we hence encounter during the course? So suppose that we have some data, right, over these variables, these predictors X. You can think of gene expression. You can think of the advertising example, whatever it is. But, here we're talking about income, years of education, seniority, and stuff like that. How much data do we have? This typically we count in integers. That makes sense. And we typically call this n. So whenever I use n, that I'm not going to do. Oops, I need to turn off my pen. So up, n observations. So this you will see in any machine learning paper the moment that there's an n, now we're talking about how many observations you have. So observations are training examples where we have data for the input, for the x's, and we have some data for the output, y, right? So the thing that we want f to predict. Typically, this looks like, well, x, data for x, first datum, this, and then the output, y1, and so on and so forth. No need to run. I mean, I'm going really slow. Okay, good. So, and what we're trying to do, based on these n data points, we're trying to find the best possible function f hat, not knowing what the true function is. But how we distinguish what we're trying to do is in two different classes. And these classes are not completely distinct. They sort of run into one another, but we call them parametric on the one hand and non-parametric on the other. Okay, let me first pop the intuition. These are functions with parameters and these are functions without parameters. No, has nothing to do with that, right? So I might ask this question in the exam. You now already know the answer. So what is it about then? It's about how many degrees of freedom does a model class have? So let's go first to parametric models. Parametric models, we know we are given a functional form. For example, linear. So here we have the same data points as I had previously, right? This is then the true function, this blue wavy thing, right? That is true. You can see the true function is not perfect. There's still some noise, right? There's still some black bars to the points because there's noise, irreducible error. But we could choose to fit this data with a parametric model, which is linear. And hence we have essentially, well, I keep wanting to point to the screen, but I should do this. We have a beta naught, which is the intercept. Then we have some coefficient beta 1 for predictor 1, beta 2 for predictor 2, and so on and so forth. Together they define this beautifully yellow plane. Is this now a good fit to the data? Well, I can promise you this is the best possible yellow plane that we can draw for these data points, but we already know that actually it should look like this, right? Good. Now, if we have chosen this form, linear, what does it mean to do, well, to estimate f? Comes down to just estimating the parameters, just finding the best values for beta naught, beta 1, and so on and so forth, right? Which is, well, a reasonably straightforward task. The problem is that if we chose unwisely, what is the form of the function, which in this case we clearly did, right? Because this is not a nice blue wave, this is a yellow plane. The best function f hat that we may attain by tweaking all the parameters to the best that we can will still lead to pretty bad prediction and possibly completely worthless inference because it points out that certain things are important where they're actually only marginally so, and they sort of missed the point, so to speak. Let's go to another approach. We still have the true function, still blue. And now what we're looking at are non-parametric methods. What are those? Those do not assume the shape of f, right? They don't say, hey, this has to be flat or this has to be quadratic or whatnot, right? No, they basically, you know what? I'm not just going to find the parameters of the function. I'm going to find the shape of the function itself as well. So non-parametric methods in that sense are, well, infinitely more powerful than parametric ones. They're also much harder to get right. So they basically have so much power, and I mean, as I always forget the name of the uncle, but the uncle of Spider-Man said, right, with great power comes great responsibility. Well, that's the problem with non-parametric methods. So, okay, what does this mean? we don't just have to choose the parameters of the function, but in a way, the function itself is a parameter. So overall, we need to estimate many, many more parameters, and hence we need way more data. How much more data? Well, if you put it really crudely, exponentially more, right? That's just from plain learning theory. That kind of ignores what is the true shape. So a lot more. That is more accurate. We need to be very careful. We need to be very careful. If we have too little data and we fit a very rich function class, non-parametric, what we may achieve, let's see if I have this figure, I mean, I can't see it because of my Zoom, perhaps I can't actually. Yes, this should be up. So, for example, here, so if we now fit a slightly, well, overpowered method for the amount of data that we have, right? Smooth linear models are terrific. We have a little bit too much data, or too little data here, right? Too many parameters to be fitted. As you can see, if I now go back and forth between the true model and the yellow one, you can see that the yellow one now fits the data better than the true model does. Well, that's not a good thing, right? I mean, that means that yellow is actually fitting the noise, which is irreducible, completely random, and hence the predictions that yellow will make, right, if a wild new data point arrives, are likely more off than the true function will. I say likely and more off because, hey, there is noise. I mean, yellow may get lucky, right? But, it's also possible. Everything gets lucky now and then. Okay, if we now plot this, a nice 2D landscape, where we have on the x-axis what we call the flexibility of a method. Not really a technical term in this particular case, but you get the intuition, right? I mean, the more parameters you have, I mean, the more, let's say, fancy the shape that you can draw through your data, the more flexible the method is. That is the one axis. On the y-axis, we have how interpretable methods are. How easy is it to look inside the black box, or perhaps the box is not even black, it's just completely see-through. Those methods with low flexibility that make relatively strong assumptions about what is the shape of the function, right? Like, okay, it's going to be linear, it's just going to be a plane. Hey, well then, if that is the function class, we know that we just have to look at the coefficients and we learn everything there is to know about this function. We know how it behaves now, tomorrow, the day after, we're done. Okay, so which methods will we consider that fall into this regime? We'll have subset selection and lasso. Lasso we will see next week or the week after already. Those are methods that have very high interpretability. So they make relatively strong assumptions about how they think the data looks like, and hence low flexibility. But we know exactly if they find something, why certain things work. Right? So you have a nice trade-off there. Let's throw a few more methods onto the screen. Least squares is going to be the method that we'll be exploring in the next 2 weeks before I arrive at lasso. A slightly higher flexibility, and as a result, yeah, we know a little bit less about what it's doing always. Then we have generalized additive models, one of my favorite classes of models. Trees and forests, very flexible, can basically almost do anything. Then we have bagging and boosting, which basically takes any of those and just builds like one happy family of them. And well, together they have 2 heads is better than 1. Well, let's extrapolate this. 15 million heads is better than 2. Something like that. That is roughly what bagging and boosting do in a smart way. If I were to draw, I don't think I have it. Oh, yeah, actually I do. Very good. The 2 most powerful classes of learners that we're going to see in this course, and you could say so far exist, are support vector machines and neural networks. And you could say that, well, neural networks now also counts towards deep neural networks, but perhaps deep neural networks, the deepest are somewhere here, right? That's interpretability, just you can throw it out of the window. It's impossible. Everybody is trying to get, why are you doing this deep neural network? My group included, and we're achieving some successes now and then, but in general, I believe this problem is just simply unsolvable. Perhaps we can discuss this at one moment in the break of a lecture or so. But, main point is, with great power, yeah, you lose interpretability. That's roughly what it comes down to, right? There's no free lunch in that regard. Why would we then prefer a more restricted model over a more flexible one? Yeah, if we don't have so much data, if we really care about learning about it, we want to be able to use this model to make predictions and understand what it's doing. Let's go back to here, actually. Suppose that we now have, let's take COVID. COVID is a great example. I should have made a slide about this. There was recently a study posted that out of the, how many, I think it was 1,046 research papers put out since the start of the COVID epidemic, as it was in the beginning, and trying to use machine learning, right, the power of AI to predict if somebody suffers from COVID and how bad it's going to be and if they're going to survive or not, and so on and so forth, right? And we're going to leverage the power of machine learning to do this prediction, right? Because doctors, what do they know? Out of these 1,046 different top-level publications, I mean, across all sorts of medical journals, machine learning and whatnot, at the top of my head, there were, I think, 211, low 200s, right? That were actually somewhat, well, replicable in the sense that there was either software available or it was easy enough to, well, based on what was written, to recover it. The 800 others, like, okay, voodoo, right? Pure voodoo. Okay, 211 methods that can save humanity, right? And beat this pandemic. So this large team actually tried to implement and apply on data. 46 or around that number actually did something, in a sense that did not crash and burn and well, just gave random things. In the end, an absolute zero were clinically applicable. Why? Well, if they were actually tested into a real setup, turned out that the accuracies that people reported in the original publications, they were based on, well, let's say X-ray scans, right, of people's chests. And is this somebody who suffers from COVID, right? Are these white patches? We've all seen them, right? And it turned out that they were training their machine learning models, often based on deep learning, but I don't want to pick at deep learning specifically today. So they had the one class of people who actually had COVID, and they had another class. You also need to have some examples that people that don't have it. And well, one of the major mistakes that people did or made was that for these they used, well, real live COVID patients, right? Often the quality of these pictures was kind of bad, right? Not to say shitty, because, well, everybody was in panic. And for this, many researchers used the same set of X-ray scans of people not having COVID. And how do you know this? Well, they're older, right? And you need to download them somewhere, because now really separating out, you know what I mean? Let's find out if people have lots of work, right? Let's just download the data set. What is the most commonly available data set out there? Children X-ray photos. So in the end, there is, well, perhaps 45, and perhaps the 46 did something different, 45 beautiful methods out there which can separate adult X-ray scans from children X-ray scans. Right? So this is one of those things where interpretability is kind of important. There's also others. I mean, that colleagues of mine, of ours, I should say, in Darmstadt, Christian Kersting's team, they also had a beautiful study, basically in a similar direction, where they wanted to figure out what is this deep neural net now actually looking at in these photos, right? What is it trying to make its decisions on? Again, this is almost a voodoo science, really difficult to get your fingernail behind. If I really crudely misrepresent what they did, they essentially trained the system on these X-ray images, right? And then, well, blotted out parts of the image just to see, does the decision change? Turned out that if you avoid this children X-ray versus adult X-ray, right? So you have two sets of adults. The system often learned to read the marker in the bottom left corner or the bottom right corner. Right? Yeah, well, great, right? I mean, that's exactly what you don't want to do. With great power comes great responsibility. I say this not just to bash these very powerful methods, but mostly to instill a little bit of well, humility, but also fear in all of you, right? Machine learning is a beautiful hammer to swing, but in the end, I mean, the beautiful principle of shit in, shit out holds everywhere in engineering, right? You really need to think really carefully about what data am I going to train on, what assumptions do I make, how am I going to test whether it actually does something for real. And yeah, just downloading some data set from the web in an attempt to save humanity, it might work or not. Good. Okay, now let's get back to the actual story I wanted to say, because I have this habit of then meandering and running out of time in the end. So let's see if I can catch up again. Yeah, so get back to, so if we have highly flexible methods all the way to the end, we need a lot of data. And it needs to be good data too, but we need a lot of data. That is one of the reasons why you might say, well, I would love to train a support vector machine or a neural network, but you know what? Today, I'm not going to do this. I just said that I should not meander too much. I'm just going to do it again. I'm going to do it again. But, this is just a story I love so much. And I need to share this with you. That's also to show that the basic things that we're going to be discussing in the next few weeks, they really do matter. They really, really do matter. I'm involved in a project together with some other people at CISPA, together with the German Cancer Research Center, DKFZ in Heidelberg. And the project is about, well, I'm skipping lots of details, but essentially there is one particular nasty type of throat cancer that, well, if you have it, that's really bad news because it is almost untreatable and it will most definitely kill you. However, that's then the good news. There is a drug that if it catches on, you're good, right? You live a happy and long life. That's no problem. The bad news is that the drug can also kill you even more quickly and more painfully. So you don't, as a doctor, right, when you have like, well, the Hippocratic Oath, right, you don't want to just like, okay, everybody gets a pill, right? I mean, you don't want to do that. Now the question is, why does it work for certain people so well and for others it doesn't, right? That's what they want to find out. And doctors are not stupid, right? So we should not just assume, like, give us the data and machine learning is going to solve it. No, they know their stuff. They know their stuff. So they, for example, have figured out that people who are positive for humanopapillovirus, HPV positive, so somewhere earlier in their lifetime, they encountered this virus and survived. I'm not a medical doctor, I'm not a useful doctor, so I don't know how good or bad having this virus is. But if you've had it, and you now suffer from this particularly nasty cancer, then this drug is most likely going to save you. That's good news, right? So you kind of want to have had this humanopapillovirus. However, there's also people who never had HPV and also respond positively to this drug. Well, yeah, you kind of would like to give the drug to them too, but yeah, that catches a lot of people who would die in a horrible way. So we don't want to do this, right? Can we use machine learning in one way or another to figure out, I mean, well, what is the subpopulation? What do these people have, right, that are not HPV positive, but do respond positively? What separates them from the people that don't have HPV and, well, would die a horrible death, such that we can treat very targeted, right? I mean, to the point of almost personalized medicine. Okay, so it's a cool topic, right? And that's at least I think so. I'm really happy to work on this. If we can build a system that can actually do this, so far I'm very optimistic, we can really actually save lives, right? So this is cool. So in the first project meeting, this is what the story is about. We were there with a group of people, I mean, machine learners, lots of computer vision people who love deep learning. And well, the problem was sketched. Cool. That's yeah. So how much data do we have? Yeah, well, we have right now, we have a lot of data. We really have a lot of data. We have 162 samples, but we think that over the course of the next, I think 2 years, I'm paraphrasing a little bit, right? I don't have all the numbers exact. We'll have 300. You could see the deep learning people who are used to having millions of training points because deep neural nets have millions of parameters, and hence, well, you really need those. Otherwise, it's just going to be make-believe. They sort of became a little bit more pale, like, oh yeah, okay. How many predictors do we have? How wide is the data, right? In images, I mean, just in M by N, right? I mean, and then lots of colors and what. They're used to lots of features, and neural networks love these support vectors machines. Whoops, where are we? Love these too, because then they can find all sorts of dependencies, and that's what they exploit. That's what the power of it is. Yeah, we have a lot of features. We have 42 features, which is absolutely nothing for these types of methods, right? So basically, we have a problem domain, which I hope you agree would be really cool to solve. What are the causes of, well, why does this drug work, yes or no? There is definitely a data problem there, but it's not one that these super flexible methods can solve, right? Okay. I'm not going to tell you either today or in the next few weeks what methods we're investigating that actually has a chance, but it comes, I mean, on this line, it's, I think, somewhere here-ish. It's pretty inflexible, but pretty damn cool. Maybe we get to it again in a break. So with few observations, possibly few predictors, you may want to choose something that's a bit less flexible, but actually has a chance of teasing something out of your data. Good. What do we have next? We have, yeah, supervised versus unsupervised learning, just as a sort of a quick swoop over what is out there. In supervised learning, which is the setting we'll be considering in the first half of EML, hence I'm teaching this, which is a bit weird because I'm more of an unsupervised person, but okay, that is fine. I know this too. The idea is that we get a lot of training data, and a lot could be then tens, hundreds, or millions of data points where we're both given the values of the predictors of the x's and the desired value y. And then the job is relatively simple, just find that function that predicts y as possible. Right? There's also a setting called semi-supervised learning, which I find really interesting because it comes much closer to, for example, medical reality, where we're given only few labeled samples, right? So we have few cases where both x and y are given. And in addition, we have a whole bunch of data where we do have the inputs, but we don't know actually what the output is. Particularly in medical settings, right? I mean, you're not going to put everybody through an X-ray and this and that. I mean, just lots, that would be super costly, right? And then especially, I mean, just opening somebody's brain just to see, okay, I mean, what happens if I poke here? You don't want to do this with everybody. But we're not going to be talking about semi-supervised learning, but I do want to point out that it exists, right? Just that the thought like, hey, couldn't we use this? Yes, we can, but not in EML. Then unsupervised learning, my not necessarily first love, but my heart yearns for it. There we're just given these x's. Already at the beginning of the lecture, I already quickly covered these clustering problems. Here I'm going to somewhat revisit this just to show how difficult numbers of clusters, what are these distance functions, how is this are. But I suppose that if I would point at a random person in this audience, don't be afraid, I'm not going to do this, and I would ask you to tell me how many clusters there are, or somehow point at them, define them, you would probably say something like, this is one, there's one over here, there's one over there, right? And perhaps you would even say, you know what, the top left one, blue, to the right is green, and to the bottom is orange. And you would be absolutely correct. That would be terrific. That would be terrific. If your data looks like this, life is easy, right? I mean, easy peasy, Bob's your uncle. I think that's the expression in the UK. In real life, data often looks way more like this. And there are still 3 clusters. And if I were to ask you, okay, which are they? Having told you there are 3, you probably will be able to find them, right? I'm going to now point at Alex, not for him to answer the question, but he mentioned density earlier. You can see, if you look through the hairs of your eyes, that there is sort of this more dense area here and over there, perhaps. Hey, there could be 3 clusters. Had I not told you there were 3 clusters, maybe you would have said 2, maybe 1, maybe 5. I don't know, right? But, okay, so clustering is difficult, very difficult. We need ways in both cases. So now I go back to the predictive case. We need ways to determine what is good, what is bad. Does a function fit well? Is a clustering good? Is a predictor good? And so on and so forth. How are we going to measure this? We already decomposed the squared expectation, the difference between the predicted value and the true value, right? This bias-variance decomposition we saw earlier. We're going to be looking a little bit further into this and give you some examples to show that, hey, this is not, it is very basic, but it's not easy. So what we could do is now for every data point, let's go back. So for every data point, so from I is 1 to n, we now measure what is the difference between the true output value and the one that we predict, right? What f hat thinks that it is based on x. And we square this error and then we normalize it. Well, that's the average squared error, and we call this the mean squared error, because actually it is the mean and not really the average, but okay, I'll let that slide for myself. This we can compute very straightforwardly on the training data, right? On the data where we know what the desired output is, that's where we can compute it. Which is nice because it allows us to, well, tweak the parameters or the shape of f to the point where we bring this MSE down. But it's also kind of useless because, for this data, we already know what the output should be, right? And if we tweak the shape and the parameters of f too much, we're going to be overfitting. We're going to be following the noise too much that we don't want. What we're actually interested in is the test error. What would the performance be of our function f hat if we would let it loose in the world, right? On data we haven't seen yet, on COVID X-rays that come in tomorrow, or in a month or whatnot. How do we measure this? That is basically what we would like to have. And so X0, or unseen data, right? I mean, patient comes in tomorrow. What is going to be the average over the square distance between f hat and the thing that we can't know? We will somehow need to estimate this, right? So we don't just need to estimate the shape of f and the parameters of f. We also need to estimate how good f is actually going to behave. There's a lot of estimation involved in machine learning. How do we call this quantity? Well, the test error, the generalization error, the expected prediction error, and there's a whole plethora of others. At the right, I give a few examples just to show you why this is important. We have the black line through this point. So the black line is the true function. The dots are the points sampled from this function. And as you can see, there is some noise, there's some jitter, irreducible error, right? Then we have right now you can see the blue line, which is a smooth spline. And you see the green line, which is a rugged spline. You can't see the linear model just yet. Right now you can. Obviously, the straight line is not the best fit. But let me just remove it for a second. The best fit in terms of error is going to be the rugged spline, the green line, right? Who thinks, just by a show of hands, sorry, Zoom people, that the green line is superior to the blue line? Either you're all asleep, very shy, or very smart. That's one of the three. Or you didn't understand the question. That's also possible. Clearly, the green line was overdoing it, right? It's fitting noise. We don't want that. We don't want too much flexibility. However, the green line achieves the lowest mean squared error. So it's just plainly reducing mean squared error is clearly not a good idea. So let's look at it like this. Here we have on the y-axis, we have the mean squared error that a model can achieve. And on the x-axis, we have the flexibility of the method, where we have the yellow ones, linear model, very inflexible, right? How many degrees of freedom does it have? 2. How do I know this, right? I mean, it's not because I'm that brilliant. No, linear function, it has an intercept, beta naught, and a slope, beta 1. 2 degrees of freedom, right? Easy peasy. Bob's your uncle. The blue one, the smoothing splines, that tries to bring the smoothness a bit down. It's in the middle, roughly 5 or 6 degrees of freedom, give or take. And the green one, which we all agreed, well, fits the data really well, but not really the one that you would recommend. That is the on the right-hand side. Now, what we see is that the yellow one achieves a high mean squared error, both on the training data and also on the testing data. The blue one does actually quite well on data that hasn't seen yet. And the green one, well, that does very well, does very well on the training data, but would do it very badly on testing data that it hasn't seen yet, right? So we want to balance somehow, ideally, the flexibility, so the amount of flexibility we give to a method, that we want to measure, as well as how well it's performing, right? The more flexibility I give, also the higher the performance I would expect that it gets. And actually, if this expectation in performance doesn't rise as quickly as it should, well, you know what? I want to take this flexibility back again. Yeah, so we want to balance this. This is for nonlinear data. Let's go through this again. Here we have data that is not quite linear. I mean, it's still exponential, but okay, very much zoomed in. And we still have the 3 functions that we saw previously. Right now, the linear model is a pretty good fit. The blue one as well. Okay, let's look again at this decomposition between test error and training error. And you will see that overall, so on the testing error curve, the yellow one and the blue one are now very close to one another. The blue one is still a tiny little bit better, right? So that is the best choice. Now, what are the options that we would have ideally, right? Suppose that we would be able to choose any method on this red curve. Which one would we like to have? The red curve are all possible machine learning models under certain flexibility that we could get our hands on, maybe. But obviously, we want the one with the lowest mean squared error. So in this particular case, what we actually would like, and this might be just my drawing error, I don't know, perhaps this one over here, where the laser dot is right now. That one seems to be now, just by scanning it by eye, the lowest. That's the one we would like to have. Currently not on the menu, but that might be a drawing error in this figure. So any method that we give more flexibility will start to overfit. Okay, I thought the battery just died. Good. Okay, let's continue. Now, highly nonlinear data, what are we going to see here? Okay, let's draw the line. The line really doesn't fit. Here we see that again, the curve has, it's not really quadratic, but you see that if it's too rigid, too little flexibility, it's high. If it's too flexible, it's high. This is an example with a lot of flexibility necessary, right? So the green model is not doing that badly, but what you can see is that the smoothing splines, we will see in a few weeks, they somehow magically find a pretty damn good model, right? It's one of my favorite methods as a result. Okay, so now let's skip this. Yeah, good. So let's go back to this bias variance trade-off and how does this now work? It's written slightly differently now than we had on the earlier slide, but the message is exactly the same. The shape of the curve on the right, and particularly the red curve, that was what we're talking about, right? You can explain this by breaking down what would the best function possibly do, and well, what errors would it still make? And so this reducible irreducible error idea. We have here for an unseen data point, so this is the difference for an unseen data point, and this is our prediction squared. We can break this down as the variance in the prediction of f for this unseen data point. So how certain / uncertain is the function, right? But, if you have a super flexible function, then there will be a lot of variance in your prediction. If you have a method that always just gives one value, there's no variance there, right? There's also the bias of your function. So it's always up, it's always down, right? I mean, it doesn't really have a tendency. And there's always this irreducible error. Those are the three aspects that you can break down. What is the expected squared error over unseen data? How this works, how this breaks down completely, obviously, but also consciously skip this because I want you to look into this into the homework. And in the end, the magic is well, there's not so much magic to it. And hence I want you to uncover this yourself. I will say a few more words though. The bias term, so we have the variance of the function, we have the bias term, and then we have the variance, the irreducible error, right? The variance of the noise. The variance of the noise, it's a nuisance. We can basically ignore it. But we now have this variance and bias. Now, the more, let me say this, let me actually also take a sip. The bias is the, what it says me, I can just mean do PowerPoint karaoke, the systematic deviation of the estimate of the true value. So is there really, is it like always off all the time? Variance is, what is the variation between different training sets? Okay, let me work it down from the bottom. Suppose that I now say, you know what, I ask, see, actually I should have asked more names because now I only know Alex's name and I don't want to pinpoint him all the time. That's anyway, I'm just going to ask. If I were to ask you, actually, what is your name? Deborah. Okay, if I were to ask you, Deborah, you know what, we're going to be fitting a quadratic function through some data, right? But, now, obviously, if I give you this data set, or if I were to give you that data set, and I'm not going to be mean, they're not going to be the same secretly, right? They're going to be different, then, well, probably Deborah is going to find different quadratic functions that fit this data best, right? But, okay, so suppose that I now would give you two data sets, but this data set is almost the same as this one. Almost. Well, the function that you will find would also be very similar, right? But, okay, very good. Now, that is where's the intuition, if the function would be the same, would be similar. Because for quadratic functions, sure. Suppose that we now that I allow you like a super squiggly function, right? With lots of degrees of freedom. would it still be very similar, or could it be a very different function that you find? It could be similar, but it could also be very different indeed. No, so the moment I allow you to really fit all the data points, and there, even if there's a small difference in the data, I mean, all of a sudden, you could have a very high variance. So the prediction, so the function f that you would find over your training data, that would vary a lot, right? That is, so different training sets would give something very different. It would really get a different function. Now, what is the bias term then? Suppose that the true data, I'm going to give Deborah, is actually cubic, right? And that's, but I only allow her to fit a linear function. What is poor Deborah going to do? I mean, she's going to try to find those coefficients that minimize the error, right? Yeah, I would do so too. But given that I gave her actually a cubic function, the one that she comes up with will never be, well, really close to the true one, right? And that's there is a systematic bias that she just cannot escape, no matter how much she does her best, right? That is the bias term. Now we have a trade-off. The more flexibility I give to you trying to fit a function, the lower this bias term becomes, because the closer you will be able to get to the shape of the true function, right? I say can, because you only get limited data from me, so you might, I might pull a fast one on you. And then the second term kicks in, the variance. Because if I allow you a very flexible method, and yeah, well, on this data set or that data set, you will find different models, right? This is exactly what we see here. The linear models over here for moderately nonlinear data, yeah, they're just simply unable to fit the data well, right? But, so they have a high bias, but a low variance, right? Then here on the right-hand side, the green method, so these rugged splines, which we're not even going to cover in the lecture so much, they're on the other extreme. They're very flexible, very low bias, right? They can fit, if I give you enough data, they can fit any function perfectly, right? They're the best splines ever, except that when you don't give them enough data, then they overfit like hell. There's a very large variance, right? They cannot tell apart two data sets that are actually very similar. They're like, oh, no, not to me. No. Very high variance. So this slide and this concept, this bias variance decomposition, is one of the most important concepts, not just in this course in EML. We'll see it time and time again. This is really underpinning almost all of statistical learning theory. And statistical learning theory is basically the only full-blown theory we have about how we can learn from data. It is also in recent years shown to be, well, limited. Some of you might have heard about the double dip phenomenon, right? And learning from using deep neural networks. I mean, they will also start like this. So if you have a very small network, and oh yeah, and then, well, if you make the network too deep, right? And that's oh bad, and yeah, well, in certain cases, all of a sudden, whoop, it will actually go really down. All of a sudden, it does perfectly. There's lots of theory now, and we're trying to patch this up on why this is the case, but it's not explained by classical learning theory. And you really need, well, a lot more understanding about how can we learn from data to begin with. So we're going to ignore this double dip phenomenon here, right? It does not exist, right? We're going to just single dip. Good. Last minute or so, perhaps two, I don't know. Let's now look at how can we decompose this testing error, right? These red curves that we saw previously, and ignoring the training curve. We're not interested in that anymore, but we're now going to decompose it into the variance term and the bias term. That's what we have over here. So we have the three examples we saw earlier from left to right. And so we have this, oops, back, so up. We have this U shape. And as you can see, if the method is too inflexible, it has a high bias. And then as long as the flexibility goes up, at one moment it will start to flatten out because we have enough flexibility. We can fit anything. However, because we're given more and more degrees of freedom, we would actually need more and more data to tune everything in a reliable way, right? So on the right-hand side, we're given too much power for the data that we actually have, right? So the variance goes up, and that's the orange curve. Then you can see for the other two also how this now goes hand in hand. For if the data is the middle one, let me just cover this one. It's almost linear, so hence already at flexibility of 2, we're almost good, right? And then if we give more and more and more, at the bias term, we can't gain anything there anymore, right? We want to gain about this expected error. We want to bring it as close as possible to the true one. There's no way we can gain anything on the bias term. There was already almost no bias. But what we are doing by adding more flexibility, we're creating, in a way, more error, more uncertainty on the variance term. Okay, good. Yes. Wait, could you? I can't hear you. I'm gonna.
So which of these would be like the best function?
Okay. So what is the best function? Well, the best function is the true function, of course. But that goes without saying. That is almost cheating. Now, I identified, based on this decomposition, with the dashed line, the vertical dashed line that you can see, right? That so for the left image around 6, for the middle image around 3, and for the right-hand image around 10, right? That is the model. That's the right amount of flexibility of the true function. So basically, given that we generated this data ourselves, we know how many degrees of freedom does the true function have, and yeah, our learner doesn't need anything more, right? So, but it's always the one that where the dip, the lowest point of the red curve. That's the one where you would like to be, and this is where then those values actually are. Yeah, does that answer your question? Very good. Okay, so this was for regression. Regression in the sense that we want to predict a certain value, like, well, what is the height? What is going to be the amount of sales? Stuff like that. There's also the task of classification. We want to say, okay, is this an apple or is this a pear? It's a binary choice. Could also be categorical choice. Is an apple, a pear, banana, and so on and so forth. But yeah, we don't allow for pair apples, right? It has to be the one or the other. How do we measure how good a method is then? It's very similar as previously, it's just made more simple. We still sum from over all our data points from 1 to n, we normalize, and right now we just simply see, did it spit out the right answer? If yes, it gets a cookie, otherwise no cookie, right? And then, well, how many cookies did it get? That is essentially the accuracy or the prediction error, depending on how you count the cookies. Good. The base classifier, actually, no, I'm going to do this next week. I'm going to do this next week. It's already almost 6. Here it's even more, almost 6. I don't want to talk about classification anymore, unless you really want me to, right? If everybody says, yeah, slightly more enthusiastically than I did, then I will do it. Otherwise, let's continue next week. Okay, see you next week. I agree.